So having developed systems of logic in earlier sections, we're finally going to get to a topic that most people expect in a math class, namely numbers. We're going to systematically describe what the natural numbers are and what their important properties are. The following construction of the natural numbers can be done entirely within the language of Zermelo-Fraenkel set theory, but we're going to use the Peano axioms. They're a bit more intuitive and easier to work with, although I do wish to caution you, don't rely too much on intuition or existing knowledge about how numbers operate. We are trying to develop them axiomatically and formally proving as much as we can. The natural numbers are defined to be a set. We represent this set with this capital N with a double bar. And this set has the following properties, all of which we have to declare as axioms. So first, much like the first axiom of set theory was there is a set, well, now that we're axiomatically describing numbers, there is a number, and this number we call 0. We also have an equivalence relation on the set of natural numbers with the equals sign. Okay, so any number is equal to itself. If A is equal to B, then B is equal to A. And if A is equal to B and B is equal to C, then A is equal to C. This equality is reflexive, symmetric, and transitive. If you look this up online, Peano Axioms, this is frequently given as 3 separate axioms, but because we already have the language of equivalence relations, I'm just condensing it into one. There's also a function. This function inputs natural numbers and outputs natural numbers, so the domain is the natural numbers, as is the codomain. We call this function the successor function. So if I want to talk about S of n, I would call it the successor of n. What it's essentially standing in for is the number that comes after n. This function is injective, so specifically, if two numbers have the same successor, they were the same number to begin with. If S of A equals S of B, then A equals B. But also, we can phrase this through that contrapositive formulation that if A is not equal to B, if two numbers are not the same, then the number which comes after them, their successor, are not the same. But with the successor function, we also have this following property. There is no number whose successor is 0. In the natural numbers, 0 is not the number that comes after anything. Okay? We're only describing the natural numbers, not other sets of numbers. And if we're trying to describe what number comes after what, we are declaring that there is no such number, so that after that number comes 0. So the natural numbers can now be developed as a bunch of symbols. Okay? We can actually describe a great deal of what goes on in the natural numbers just with those axioms about equality being an equivalence relation and how the successor function operates. So for example, since 0 is a natural number, that was our first axiom, its successor must be a natural number. Since no number has its successor being 0, S of 0 can't be 0. That would violate that there would be something whose successor is 0. So whatever the successor of 0 is, it's not actually 0. So whatever the successor of 0 is, we need a new symbol for it, and we're going to give it the number 1. We're going to use that symbol is standing in for whatever the successor of 0 is. Next, 1 is a natural number, and therefore its successor must be a natural number. However, its successor cannot be 0. Okay, so whatever the successor of 1 is, it can't be 0. How do I know this? Because one of our axioms was nothing has a successor, which is 0. The successor of any number cannot be 0, so whatever the successor of 1 is, it's not 0. But it also can't be 1. Since we declared 1 to be the successor of 0, and 0 and 1 are not the same number, the successor of 1 cannot be 1. So whatever the successor of 1 is, it's not 0 and it's not 1. We're going to need a new symbol for it, so we're going to call it 2. Similarly, we keep going. Since 2 is a natural number, its successor must be a natural number. Its successor can't be 0 because nothing has a successor which is 0. Since S of 0 is already 1, S of 2 can't be 1. Since S of 1 is already 2, S of 2 can't be 2. So whatever the successor of 2 is, it's not 0, it's not 1, it's not 2. We need a new symbol. We're going to call that 3. And so forth and so forth and so forth. Okay. So we can already start to work out what the various natural numbers are. Now, some of you might be thinking all we're doing is adding 1, but I'm going to throw a big giant penalty flag on that because we haven't even defined what plus is, or what plus means, or what that function would behave like. All we're doing is describing this successor function. Okay, so since S is injective, it is bijective onto its range, which is a subset of the natural numbers. Okay, so the range of the successor function is a subset of the natural numbers. That was part of how it was defined. It's injective, which means it's bijective onto its range. 0 is not in the range of the successor function. Okay, this was one of our axioms. Therefore, the successor function establishes a bijection between the domain, the natural numbers, and its range, which is a subset of the natural numbers, but not all of the natural numbers. So we can establish a bijection between the domain, the natural numbers, and the range, a proper subset of the natural numbers. So there is a bijection between the natural numbers and a proper subset of itself. By definition, this means the natural numbers must be an infinite set, because we could construct, axiomatically we constructed, a function, the successor function, that establishes a bijection between the naturals and a proper subset of itself. So even with only the few axioms we have, we can start declaring symbols for various elements of the natural numbers, and we have shown that the natural numbers are an infinite set. But there are more axioms other than the ones we've introduced. So, sixth axiom. This one's pretty important. It says, if you have a subset of the natural numbers, that subset contains 0, and if anything is in the subset, then the successor must be in the subset. So the subset of the natural numbers has 0, and anytime you have a number in the subset, its successor must also be in the subset. We axiomatically say that subset is all of the natural numbers. This is known as the axiom of induction. It's going to be a very important thing for us. Okay. So if a subset of the natural numbers contains a 0 and always contains successors of anything, well, since it contains a 0, it must contain its successor, which was 1. Since it contains 1, it must contain its successor, which was 2. Since it contains 2, it must contain its successor, which was 3, and so forth and so forth. And what we're saying by this axiom is, you must get all of the natural numbers by continuing in this way. So, the content of this axiom is that this procedure of starting with 0 and always proceeding through successors gives you all the natural numbers. Now, we already knew the natural numbers had to contain all of these successors. What this axiom tells us is that if that's all you do is have a subset that has 0 and has successors, you actually get all the natural numbers. In other words, this process of going 0 is followed by 1, is followed by 2, is followed by 3, and so forth, that gives you all the natural numbers. There isn't anything else to worry about. There's no random other element, x, that is floating around that is different from all of these numbers and is also a natural number. The axiom of induction tells us that this procedure of starting with 0 and proceeding to the next number and so forth gives you all the natural numbers. There are a few more Peano axioms that have to do with operations plus and times. We are not thinking of these intuitively. Okay, if I say what's 2 plus 3, you shouldn't say 5. You should say I don't know because we haven't even discussed what plus is. And all we're going to do is define a few axioms. Okay? If a and b are two natural numbers, so is a plus b. If a and b are two natural numbers, so is a times b. So whatever these mysterious functions plus and times are, they input two natural numbers and they output another natural number. The plus function has this property right here. If you have a natural number a plus 0 is always going to be a. Well, what about 0 plus a? We don't know. Okay, a plus 0 might be something entirely different from 0 plus a. We have no idea how this function works. We're just declaring a few axioms and then we're going to prove everything else. Okay, since a plus 0 gets a special axiom, a plus 0 equals a, A times 0 gets another axiom. A times 0 is always 0. Okay, we are declaring these as axioms. These are not things we're going to prove. In fact, you could not prove them. That might seem weird. How can we not prove that A times 0 is 0? Just remember, throw out all of your existing knowledge and intuition. This times and this plus are entirely new functions with no properties that you are familiar with. So we're declaring a few axioms to start with, and then we're going to prove the rest. We also want to establish how these functions interact with the successor function. Now here's one. If I add a and the successor of b, what I must get out is the successor of if I had added a and b together. A plus the successor of b is always the successor of a plus b. A times the successor of b, on the other hand, is a times b plus b. These two axioms give us interactions between how addition works with the successor function and how multiplication works with the successor function. So formally what these are, they're operations on the natural numbers. They input a pair of natural numbers and output a single natural number. Okay, but if I wanted to use functional notation for addition, I would do something like this. The plus function acting on the ordered pair 3, 6 should output the number 9. And this is actually what's called Polish notation. Plus of 3 and 6 equals 9. We instead use the more familiar notation 3 plus 6 equals 9. Now, some people might look at this and say that's a really weird way to write addition. Polish notation, or its cousin reverse Polish notation, which simply puts the plus sign on the right rather than on the left, have some great benefits, but they're so unfamiliar to most people that it's generally counterproductive to try to work with them. So anyway, these axioms codify the rules of arithmetic and how they interact with each other and with the successor function. Plus, we've thrown in the only number that axiomatically we know exists, 0. Notice I have no axioms here that tell me things about 1 or 7 or 98. Okay, the only number that was axiomatically declared to exist is 0, so it's the only number that shows up on its own in these axioms. Okay, so these are it. These are the axioms. From this list of 12 axioms, we're going to prove everything we possibly could about the natural numbers. So let's get to it. Okay, we're going to start with a simple proof. It's a classic, and we really can't resist the urge. 1 plus 1 equals 2. A lot of people are going to roll their eyes. A few more are baffled. Of course 1 plus 1 equals 2. We already know that. But remember, the plus function is not what we're used to thinking of addition. It has nothing to do with counting. It has no relation to physical objects. This is just some abstractly, axiomatically defined function on the natural numbers. So if I take the natural number 1 and the natural number 1 and I feed them into this plus function, what do I get out? It's going to be 2, and we're going to be able to prove it only using those 12 axioms. So we're going to have to restrict our existing knowledge. Now 1 was defined to be the successor of 0. So 1 plus 1 must be 1 plus the successor of 0. Okay, we are using the principle of substitution, which has to do with set theory, and these are sets of objects. So here is 1, here is s of 0. Since 1 and s of 0 are the same thing, we're just substituting. But the 11th axiom stated that the successor of a plus b is always a plus the successor of b. So notice what we have here. A is 1, b is 0. So on the right, we have a plus the successor of b. By the 11th axiom, I can replace that with the successor of a plus b. And if this is a, 1, and this is b, 0, we get this. 1 plus the successor of 0 is the successor of 1 plus 0. The 9th axiom, however, said that for any number, a plus 0 equals a. So in here, we have 1 plus 0. 1 plus 0 must equal 1 by the 9th axiom. Okay, so s of 1 plus 0, the successor of 1 plus 0, must be the same thing as the successor of 1. And we defined 2 to be the successor of 1. So only using the axioms and no prior knowledge, here's what we were able to put together. 1 plus 1, well, 1 is the successor of 0. Axiomatically, 1 plus the successor of 0 must be the successor of 1 plus 0. 1 plus 0 is axiomatically 1, and the successor of 1 was defined to be 2, so overall, 1 plus 1 equals 2. Okay, let's work on something that's a little less straightforward. The successor of n is always n plus 1. Of course, many of us had already noticed that's what the successor function did, but it wasn't actually declared as an axiom. Instead, we can now prove it. Okay. So while we do know that 4 plus 1 is a number and 12 plus 1 is a number, we don't really know formally what they are yet. Okay. Also, we have not made a claim about a specific n. If I just wanted to prove that 5 equals 4 plus 1, I could duplicate the proof from the previous slide with a few more steps. Instead of going from 1 plus 1 to get up to 2, I'd have to go from 4 plus 1. It would take a while, but we could get up to 5. But that wouldn't really finish the proof here. The claim is not that for some specific n, s of n is n plus 1. It's that for all of them, s of n is n plus 1. And we know there are infinitely many natural numbers. So even if I were to prove it for a few specific numbers, that wouldn't really be much progress towards proving it for all of them. So how are we going to account for all natural numbers? We have to use the axiom of induction. The axiom of induction, recall, said that if a subset of the natural numbers contains 0, and has all of its successors, then it must have every natural number. So formally what we're going to do is we're going to make a statement. Okay? P of n is true whenever a number n satisfies s of n is n plus 1. We are claiming the truth set for this statement, the numbers for which the successor happens to be equal to n plus 1. We're claiming the truth set is all natural numbers. So we're going to define the truth set of this statement to be the set A, and then we're going to show it contains 0, and if it contains a number, it must contain its successor. Axiomatically, that will tell us that set must be all natural numbers. Well then, let's get to proving it. We've got this predicate statement. P of n is true whenever the successor of n is equal to n plus 1. And we're going to claim that this statement is true for every natural number. The inductive axiom said, if you have a subset of the natural numbers which contains a 0, and whenever you have a number in it, you also have its successor, then you can conclude your set was all natural numbers. So specifically, we're going to show that our truth set satisfies these properties. Specifically, we need to show that 0 is a specific number for which this is true, and if this is ever true for n, then it is also true for its successor. Once I've satisfied those things, the inductive axiom will say that the truth set is actually all natural numbers. In other words, this is always true. The first step was to show this statement is true specifically for 0. So instead of working with a general n, I'm going to replace that with 0. S of 0 is 0 plus 1. We do not know this is true. We are trying to prove it. So let's do that. Now recall that S of 0 was given, by definition, the symbol 1. This was just a declaration of what the symbol 1 meant. It was the successor of 0. Axiom 9 was that a plus 0 is always a. If a happens to also be 0, a plus 0 equals a. 0 plus 0 is 0. Axiom 11 was that the successor of a plus b must be a plus the successor of b. And if a and b are both 0, the successor of 0 plus 0 is 0 plus the successor of 0. Now we can take all of these things and put them together. The successor of 0, well, 0 happens to be equal to 0 plus 0. That was this line right here. So I can apply the successor function and get this. Then we can use this line right here. The successor of 0 plus 0 must be 0 plus the successor of 0. And we defined the successor of 0 to be the symbol 1. So since the equal sign is transitive, overall, the successor of 0 really is equal to 0 plus 1. That's the statement we were trying to prove. In other words, P of n is true on the specific case that n is 0. Next, what we need to do is show that if our statement holds for some number, then it is also true for its successor. Specifically, if our desired statement is true for n, then it is true for s of n. So I am plugging, in this line, I'm replacing all of my n's with s of n's. If it's true here, then hopefully it's also true here. But notice that's a conditional statement, and we can prove it as a conditional statement. We get to assume the hypothesis, S of n really is n plus 1. Then what we need to do is do a direct proof. Using this assumption, can I get to this conclusion? Well, here are the important observations along the way. Very similar to how we did the previous thing. If I add 0 to the right, I don't change the value. So whatever S of n is, I don't actually know yet, but S of n plus 0 is the same thing as S of n. Also, the successor function distributes across the sum by saying S of a plus b is a plus S of b. Here, a just happens to be the successor of n, and b is still 0. So the successor of a plus b is a plus the successor of b. And we can combine those observations as follows. Now, inside the big parentheses, the successor of n is the same as the successor of n plus 0. So S of that is S of that. Now I can distribute this S using this observation here. The successor of n plus 0 must be the successor of n plus S of 0. But remember, S of 0 was simply 1. That was the symbol we gave to S of 0. So overall, the successor of S of n is S of n plus 1. Having assumed this hypothesis, we were able to derive this conclusion. We have completed a direct proof of this conditional statement, if something, then something else. But that's the other half of using the inductive axiom. Step 1 was show that it's true specifically for 0. Step 2 was if it is true for some number, then it is true for its successor. So by the inductive axiom, the truth set must be all natural numbers. So our statement is always true. The successor of n is simply always equal to n plus 1. And from this point forward, we're kind of going to let the successor function 9 times out of 10 float away to the background. Whenever I want to talk about the successor of n, I'm instead just going to say n plus 1, because we have proven that S of n is exactly n plus 1.